Hi, this is Austin. This is the Midnight Sun Rally final for AI and data analytics. The objective of this final was to create an AI autonomous driving slot car. The car must race 24 hours. Timetable was approximately 3 months with a team of 2. Unfortunately, my partner quit on me, so this ambitious project was attempted solo by myself. The model I decided on was a camera machine vision system. Utilizing an overhead USB camera, the car is tracked via camera footage. The camera connects to a laptop. Laptop processes a video feed using a Python-based program called OpenCV. In OpenCV, predetermined bounding boxes would be drawn over curves. Curves demanded the car be slowed down. The elapsed time of the car in the bounding box would be measured and sent to the AI algorithm. The software side was a jumble of various programs forced to work together. At times, there was little direction or examples. Python 3.8.1 was used due to Python 3.9 not being compatible with Pytorch and TensorFlow. For AI processing in Python, TensorFlow, Keras, Matplotlib, NumPy, Pandas, and Pytorch were used. For processing AI using parallel computing on the graphics card, CUDA and CUDIN was used. The slot car is powered via 12-volt DC from small brushes underneath. The black chassis was designed in SOLIDWORKS CAD and 3D printed out of PETG. The motor driver used was a L298N, which receives motor signal commands from the ESP and adjusts motor speed accordingly. The brains of the operation is the ESP32 microcontroller. A backup battery to power the microcontroller is also present in case the car loses power. On the ESP, an Arduino code waits for the PC to send motor speed commands via Bluetooth. There were issues. When the PC went to sleep, I would have to manually power cycle the microcontroller to reset it. Here's an example of the Arduino desyncing. As you can see, it prints out a weird value in the serial monitor in COM4. Yeah, I don't know what that is. On the PC, processing ID was used to send motor speed commands to the Arduino. The user input is entered via PC keyboard. It must be a 3-digit PWM value. Program shows last saved PWM value as 0 here. This was originally meant to be a test with the AI filling in the PWM value. For the AI model, I used an algorithm in Python. The original plan was to have each bounding box with 2 values, PWM and lap time. However, due to time constraints, the 2 values had to be recorded for every complete track loop. But first, we need baseline PWM and lap time data. Solo tests were conducted. The minimum PWM value was approximately 90, while at 120 the car would slide out at curves. 115 was the fastest consistent time. At the slowest PWM value, time hovered around 10 seconds, while at the highest PWM value, time hovered around 5.5 seconds. I selected the Atom Optimizer due to its speed, history with image classification, and example documentation. Atom requires 2D tensors. In the tensor I stuffed PWM value and lap time value. The code is modified from Pytorch's 2-layer ReLU that predicts Y from X. In my case, X is the max tensor, while Y is supposed to be the measured tensor. Later in the code, I call the Atom Optimizer. The optimizer guides the final tensor output towards the max tensor. I would then supplement this with training feedback, such as 2 slow lap times. However, I ran out of time and wasn't able to get around to this. This is the final output from AI code. The red input would have been actual measured PWM and lap time tensors from the camera machine vision. The red tensor is compared to the orange ideal tensor, then ran through the AI code. The number of times the AI code runs is counted with the green epoch numbers. At each epoch sample, a loss is calculated between red and orange tensors. As we can see, the more time the code is ran, the closer the AI gets to the ideal tensor value. Finally, I cherry pick with a low loss value at epoch 599. The final PWM and lap time value at the epoch is shown in yellow. There seems to be a pattern. The low-loss tensor outputs seem to be close to actual real-life measured values. Unknown if this is coincidental. Needs more testing in the future. The car started to slow down throughout the race due to tire wear. As the night went on, I had to increase the PWM value, otherwise the car would stall. There is also a sharp curve the car would slide out, denoted by the red triangle. Speed here needs to be decreased. The AI model with the tracking camera machine vision feedback would be able to mitigate these issues. In theory, the AI would process the car slowing down, then it would increase speed until it detects the car at the bounding box before the curve. Once detected, the AI would slow the car down to prevent it from sliding. The camera machine vision was not finished in time. It was explored after the race. I built OpenCV on Windows, running it on the processor. This was not ideal. Video processing ran around 1 frames per second. Needs to have the video processing run on the GPU. I pulled the image identification from a popular YouTuber named Pytorch. In the code, it uses Cocoa, the common objects in context dataset. In Cocoa, it has predefined training data for bananas. My plan was to use a banana attached to the car to trigger machine vision detection. Here are a few snapshots of the camera tracking a banana. In the Python monitor, it displays the pixel coordinates of the drawn tracking box. The red number is the object counter. It goes up as more objects are detected. Here the instructor moves around the banana. The Cocoa dataset also includes and tracks people, which is not ideal. The AI model shows promise in reeling in actual values from target values. With a little more parameters in training, it shows great potential. The car was fairly straightforward, but communication needs to be faster to the PC. The camera machine vision also shows promise. It still needs major data encoding tweaks to make it feasible though. Faster hardware and GPU acceleration in particular are needed to keep up with the car's speed. Thanks for watching. Looks like I may continue this later on at an alumni event, but we shall see. I need a better partner as well. Thank you.